Good morning, everybody. It is certainly a pleasure to be here. Let me say at the beginning that because of a scheduling problem, I arrived this morning at Domodedovo Airport at about 2 o'clock in the morning. So I am operating on very little sleep. So I hope that if I say anything that is really crazy, that you will simply say, well, he just has not had very much sleep. Let me also say that if you need any clarification, if anything is unclear, if I talk too fast, if you have a question, just stop me and just ask, okay? Okay, so what I would like to do today is to talk about a mixture of recent research and a few older lines of work that explore timescales of catchment response and timescales of catchment transport. So on what timescales does a landscape transport water? And also on what timescales does a landscape respond to inputs of rainfall? And how are we learning to measure those different timescales? And of course, the starting point for this kind of work, like most other studies in small catchments, is the principle that we can learn interesting things about how landscapes work by studying their streams and by studying the chemistry and isotopes of those stream waters. We do this because catchments are fundamental units of the landscape. So at any point along a stream, we can define an area of the land that drains to that point, and when we measure then the flow and the solute concentrations in the stream, we are indirectly measuring the integrated effects of everything that is happening hydrologically and chemically and biologically within that catchment. Or to borrow a phrase from my friend Kevin Bishop in Sweden, streams are mirrors of the landscape that reflect the physical integration of the processes in their surrounding catchments. So I'd like to illustrate this general idea in several different ways. And I'd like to begin by looking at chemical signals in stream water and their predictability on timescales ranging from hours to decades. Solutes in stream water are important by themselves, for example, if they are nutrients or if they are contaminants, but they're also important as tracers of landscape processes. So passive tracers follow the water, they go with the flow, and their concentrations tell you something about how water is stored or mixed in the landscape. Reactive tracers, on the other hand, carry signals of where the water has been and what it has interacted with. And as an illustration of the value of tracers, I'd like to consider the standard model of how storms produce runoff, which was taught for decades and is probably still taught many places today. And in this standard model, the storm flow peak of the hydrograph was assumed to be mostly new water that has reached the stream rapidly through overland flow or macropore flow. And this stream flow was assumed to be superimposed on a slowly varying old water or base flow from previous storms that reached the stream slowly via groundwater flow paths. And it's easy to see where that kind of standard model comes from. I mean, runoff typically responds very quickly to rainfall, and it seems logical that those runoff peaks should be recent rainfall. And that is what happens in some landscapes. It's certainly what happens in urban landscapes like Moscow around us. But in most humid landscapes, we now know that this standard model is simply wrong, and the reason we know it's wrong is from looking at chemical tracers and isotopic tracers. We know that if the storm flow peaks were mostly new water, then passive tracers should resemble the new water, but they don't. And unfortunately, because of the projector, you cannot see that the precipitation signal here is basically filling this graph. And the stream flow signal, on the other hand, is this very thin line. So the tracer concentrations in the stream are much less variable than the tracer concentrations in precipitation. And the only way that can be true is if what we are seeing in the stream is an average of water from many previous rainfall events. And this is true even during storm peaks. So, okay, so that's the new view of at least how the landscape is somehow functioning. But that leads to the very tricky question. It creates a new puzzle, which is, how does this physically work? How does a landscape store water for weeks or months and then release that water in minutes as soon as the rain starts to fall? And of course, different mechanisms have been proposed. People have proposed things called piston flow or transmissivity feedback or kinematic waves. But understanding this in detail and in physical terms still is difficult, and there's a lot of work to be done. And so although this has not been fully solved, I'm highlighting it to illustrate how chemical and isotopic tracers have been pushing the science forward by showing us these sorts of challenges. So these time series come from one of my favorite places on Earth, the Plinlimmon experimental catchments in Wales, in the United Kingdom. And here, my friend Colin Neal and some of his colleagues at the Center for Ecology and Hydrology collected samples every week for 30 years, and every 7 hours for about 2 years. And they analyzed these samples for everything they could, basically the entire periodic table. Most of the data we will look at today come from this small headwater catchment here, about 1 square kilometer. And it's a very wet landscape. It rains about 3 meters per year. And we're very close to the west coast of Britain, so precipitation chemistry changes a lot depending on whether you have the winds coming from the ocean or the winds coming across Britain itself. Now, sampling every 7 hours shows us all kinds of behavior that we would never see if we simply took a sample every week. So here, for example, that's a piece of the streamflow hydrograph. Here's what you measure in dissolved organic carbon if you sample every week. And here's what you measure in dissolved organic carbon if you sample every 7 hours. And you can see that the organic carbon is closely linked to the stream flow itself, but you would almost not see this at all in the weekly sampling. You also see, even during periods that a hydrologist would say are boring, there's nothing interesting happening here. But in calcium, for example, during those boring periods, you see the emergence of a daily cycle up and down in calcium concentrations. This is some kind of biological signal. But again, if you only have a sample once every week, you never see it. So this high-frequency measurement of chemistry or isotopes in stream water can tell us all kinds of interesting things that we would otherwise be missing. So in the Plinlimmon data, here is what they have analyzed for. The things that are in gray are simply in concentrations that are too low to measure, or in a few cases, they simply don't have the instruments. This is an idea of what the whole data set looks like if you plot every concentration against every other concentration for just one site. There are 2 million dots on that graph, I'm not going to go through, obviously, the details of this, right? But it just illustrates the scale of the problem of managing data like that and thinking about all of those different possible relationships. And in fact, the first thing we did with this data set was to create that scatter plot on poster paper and unroll it on the floor and crawl around on it, because it was the only way to start looking at it in any detail. Okay, but here's just a sample of what these chemical time series look like in this stream. And on the left, we have samples taken every 7 hours for a year. And on the right, we have samples taken every 7 days for a decade. So all of this here, this whole thing here, compresses into about half of that bar here on this graph. Okay? And so you can see, and this is only about half of the high-frequency data set. This is only about half of the long-term data set. And this is only for about 6 or 7 of the different elements. But it gives you some idea of the scale and the detail of the behavior that we can now look at. Okay, right. So this bar here is all of that there. Okay. Now it turns out that 3/4 of these elements have detectable daily cycles. So we have biologically active elements like nitrate, where you sort of expect a daily cycle as the aquatic ecosystem becomes more or less active. But we also have things like calcium and magnesium. And then we have crazy things like cobalt or manganese, which also vary between day and night for reasons no one really understands very clearly. And no one understands that because no one has looked, and no one has looked because no one has had the measurements. So one of the lessons we are learning is that if you simply measure things in a way that you have not measured them before, you learn something interesting. Okay. And these cycles are not driven by a daily cycle in stream flow, because as you can see, there's almost no daily cycle in stream flow because it's such a humid place. There's very little evaporation, and so the stream flow is simply not highly variable. And they're not driven by also daily cycles in deposition, because during this period, there's almost no rainfall. This is, by the way, the only period of a month long in the entire 30 years of data from this site where there was not rain. This is a very wet place. And we just happened to catch the one long dry month. Okay, now in addition to these daily cycles, of course, there are also seasonal cycles in nearly every element, including some really sort of surprising things. Who knew that there was a seasonal cycle in arsenic or lithium or molybdenum or rubidium and so on and so forth? Okay. Now, any signals like these that vary across a wide range of scales are good possibilities for spectral analysis. So what's spectral analysis? Well, if we had a beam of white light coming through the window, it would contain all of the colors of the rainbow. And if we hold up a prism, we can break that light into its different component wavelengths or frequencies, and we can project that spectrum on the wall, and if we measure the intensity of the light as a function of its wavelength or its frequency, we get a fingerprint that we call a power spectrum. And in the case of white light, which has roughly equal intensity at each color, we would get a flat line, which we would call a white noise spectrum. Now, if we have a time series instead of a beam of light, we estimate the power spectrum using the Fourier transform, which is basically fitting sine waves of different wavelengths to that time series and measuring their amplitudes, and then changing the wavelength and measuring the amplitude, and changing the wavelength and measuring the amplitude again and again and again. And so from the spectrum of a time series, we can learn useful things about its predictability. So if we have white noise, which is a sequence of random uncorrelated numbers, we will have a power spectrum slope of 0. This is a plot again of spectral power, or the square of the amplitude, against frequency, or we can do it the other way and plot it against wavelength. In any case, in white noise, you get a roughly flat line of roughly equal power as a function of frequency. And in that kind of time series, the short-term behavior is entirely unpredictable because the individual numbers are uncorrelated, but the long-term average is entirely predictable because the fluctuations are random and they tend to average out. So the long-term average will be stable and predictable, as the central limit theorem tells us. If we integrate white noise through time, we get a random walk of random steps to the left, random steps to the right, and a random walk is highly predictable in the short term because wherever you are today is very close to wherever you were yesterday. It's only one step away. But the accumulation of those random steps leads to long-term drift. And so in the long-term average becomes less and less predictable over longer and longer periods of time. Now, in between white noise and random walks, we have something that the physicists call 1/f noise, in which spectral power is inversely proportional to frequency. And so if we make a power spectrum plot, we get a slope of 1. And in terms of predictability, 1/f noise is the worst of both worlds. There's enough spectral power at the high frequencies to make the short-term behavior very unpredictable. But there's also enough correlation across multiple scales to make the long-term behavior unpredictable as well. So it's sort of everybody's nightmare if they're trying to predict things. So here are 3 time series from Plinlimmon, and I've chosen them because their behavior in the environment is really entirely different. So about 98% of all the lead that comes down in the rain is retained in the catchment and never comes through to the runoff. But here is the lead signal in the stream flow. About 98% of the cobalt that we see in the stream is produced in the catchment. It's not coming from the rainfall. And here is the cobalt signal. And here's the zinc signal. And zinc is an element for which the inputs roughly balance the outputs. So the catchment isn't retaining it, it's not releasing it. So these are 3 entirely different time series driven by entirely different chemical processes, right? And the time series look completely different from one another. But if you plot their spectrum, their power spectra are almost all the same. And they all approximately follow this 1/f noise pattern. In fact, if we look at all of the elements in this great big data set that I've been describing, there are 45 elements for which we have really good data. All 45 of them show this same spectrum on timescales from less than a day to more than a decade. Now here we're looking at 16 of those 45, and I'll notice that the stream flow itself does not follow the same pattern. The stream flow is not a straight line here, it's a curved line. And so it's not a case of all of these things simply following the stream flow fluctuations. We can also see peaks here at a frequency of 1 year. That's the seasonal cycles. We can also see some peaks here at a frequency of 1 day. That's the daily cycle. Okay. Now, when we saw that pattern at Plinlimmon, we thought, well, maybe it's just the British. Maybe they just have weird streams or something like that. I apologize to our colleague from Bristol. I know, but you are coming from Bristol, so I have to apologize, right? So then we made contact with some colleagues in France at the University of Rennes, and they have a research catchment in Brittany, in the far western part of France, that is totally different from Plinlimmon in almost every way you can imagine. The land use is totally different. The climate is totally different. The topography, the soils, they are all totally different. And our Rennes colleagues sampled stream flow at their catchment every day for 3 years, and they analyzed for lots and lots of different elements. And we plotted their power spectra, and their power spectra all basically follow the same 1/f scaling pattern that we have observed at Plinlimmon. A few years ago, Sarah Godsey, a colleague now at Idaho State University in the United States, collected data from about 20 different catchments where she could analyze the spectra of chloride as a tracer that follows the water. And in her analysis also, 20 out of 20, that is all of those sites, exhibited this same kind of scaling. So it looks like this kind of fractal scaling in streamflow is very widespread. And now we can ask the question, well, now, so what? Well, one answer to the question, so what, is that many catchment models represent the subsurface as some kind of well-mixed box. And a well-mixed box will not give you that kind of spectral scaling. It will give you a very nice spectral slope of typically something like 2, not 1. And so, in general, this scaling behavior that we have seen presents a fundamental challenge to many models that are commonly used to evaluate transport at the landscape scale. Now, the thing we know about the physical environment that water flows in is that it's heterogeneous on all scales. If we hold a block of soil in our hands, we can see the macropores. Right? If we look at the scale of a profile, we see all kinds of heterogeneity. We see vertical structure, and then we see within that vertical structure fast paths and slow paths. And so we know that this kind of heterogeneity will lead to macro dispersion. And the fact that you have gradients in permeability means that you will have a phenomenon called shear dispersion, in which the water at one level flows faster than the water at another level, so that a tracer will spread simply because some of it is in the fast lane on the freeway and some of it is in the slow lane, right? And so we ask the question, what processes can create this kind of scaling from that kind of heterogeneity? And so one very simple model of transport is to say, we'll ignore all the other complexity in our landscape, and we'll consider the landscape to be simply a profile. And we will assume that rain falls everywhere. And the rain that falls closest to the stream will get to the stream fastest and will not disperse very much because it hasn't traveled very far. The rain that lands in the middle of the slope will take longer and will disperse more. And the rain that lands at the top of the slope will take the longest and will disperse the most. And the combination of, or what you see in the stream will be the combination of the inputs from all along the slope with all of these different degrees of dispersion. And that simple process will generate the kind of fractal scaling that we've seen from pure uncorrelated noisy inputs in rainfall. And we've shown that this can also be generated by spatially spatially correlated reaction rates along the stream profile with or without chemical retardation. So there are different variants of this very simple model that will generate this kind of behavior. The other thing that will generate this kind of behavior is so-called anomalous dispersion of spatially uncorrelated inputs from reactions. Okay. Now, one implication of that simple picture of the landscape is that high-frequency signals that come into that landscape from precipitation, for example, will mostly be erased by dispersion, particularly if they start far away from the stream. So streams may be mirrors of the landscape, but the landscape itself is a red filter that tends to filter out the high-frequency behavior that is coming from, particularly from far away from the stream channel. Okay. But, so we can ask also, beyond the world of hydrological modeling and theory about how landscapes work and so on, so what? Well, another kind of so what has to do with the predictability of trends in water quality on different timescales. So here's what I mean. The statistics that we all learned in school are based on the idea that any noise in our system is white noise, which means that pluses and minuses tend to average out, so that as we collect more data, averages become more and more certain. And time series that behave this way are called self-averaging. And when I went to school, I was never taught about anything else. But it turns out that not all time series do this. And in fact, one of the very interesting properties of these 1/f time series is that they are not self-averaging. If you have a time series that obeys this kind of scaling, and you take averages over longer and longer periods of time, those averages are equally variable than averages you take over short periods of time. They're equally different from one another. Each average of, say, a day or a week or a month or a year is an equally bad predictor of the next day or the next month or the next year, and so on. Now, it seems really counterintuitive. We didn't learn this in school, but it is, in fact, the way the world works. And in fact, the phenomenon was first discovered when people were trying to understand, so it even happens in that kind of technology. But this has enormous implications for trend analysis. So if we fit a trend to a piece of a white noise time series, it will usually be consistent with the trend that we fit to the next piece of the white noise time series. So I've taken a white noise time series and I've broken it up into blocks, and I've fit trends to each of the pieces, and you can see that the different trend lines basically agree with each other. If I do the same thing with 1 over F noise, those trend lines that we estimate in each time interval are very poor predictors of what the trend looks like in the next time interval. That is, we calculate our uncertainties, we calculate our confidence bounds, and we very confidently think we know where that trend is going, and then it doesn't go that way. So, in general, even if you get a very clear trend with narrow uncertainty bounds, that trend will be a very poor predictor of what the trend is in the next time interval. And I know this is weird, but it also is true that as you fit trends to longer and longer time series, or as you get more and more detailed data within those time series, it actually makes that problem worse, not better. Because our statistics are assuming that more data reduces your uncertainty, and that's not what happens when you have that kind of correlation structure in your data. Okay. So we need to be thinking more about those kinds of possibilities as we start looking at trend data in things like water quality. Now, we can also use this kind of analysis to define some interesting timescales. So we can fit this advection dispersion model that I mentioned before to mimic the spectrum that we observe in the output in the stream, and from that we can estimate a sort of a mean residence time for this catchment of about half a year to 1 year, implying a total storage underground of 1 meter or 2 meters of water, for example. And then we can contrast that to the storage variation between low flows and high flows, which we can estimate by looking at the recession behavior after storm events. And we find that the dynamic storage, the variation between low flow and high flow, is much smaller. It's only about 100 millimeters in this system. It's only about 5 to 10% of the total storage, even though as the storage changes by only that very small amount, the discharge itself changes by a factor of 300. So the picture that emerges from looking simultaneously at this very fast response of the stream and this very damped response of the tracers, the picture that emerges is one in which, if we look at the storage in the catchment as a column, everything we normally think about as hydrologists is up here. It's the dynamic storage. It's what can fill and then spill in the subsurface. Right? But that's on top of an ocean of passive storage, of residual storage that never drains. Right? The flow in the discharge will go to zero, and this will all still be down there underground. And this is what gives the landscape its chemical memory and its isotopic memory. And it may also be biologically important. The trees may be living off of this. We now have data from nearly 1,000 trees in Switzerland showing that in August, those trees are mostly using water that fell as rain in the winter. They're not using the water that fell as rain in August. So they're clearly reaching deep for that. Okay. And here's the dynamic view of this. As we watch the stream go up and down like this, all of that is happening in this little layer of variability in the total storage. And then we have this sort of, as I said, this ocean of passive or residual storage underneath. And I'll also note that this is probably a gross underestimate of the volume that's down here for reasons that we will see in a few minutes. You will tell me when it's a good time to take a break, right?
Well, I think it's better to ask the audience if we should take a break.
We can go another 10 minutes or we can take a break now. What would you like? We take a short break.
5 minutes break.
So this slide is for our friend Dimitri. This entire data set that I've just shown you is publicly available, is open to the community, and it's been published in a series of papers. If you go to, for example, this paper here in Proceedings of the National Academy of Sciences, the other National Academy of Sciences, not the Russian one, the American one, there is an online appendix to that paper that has all the data. This is the guy who is primarily responsible for creating that data, Colin Neal. He is married to Margaret Neal. Margaret Neal was the director of the laboratory at the Center for Ecology and Hydrology. And I like to say that if you are ever going to try to do that kind of analysis, it helps to be married to the manager of the laboratory. But then the challenge is to remain married to the manager of the laboratory, and somehow they have done this. So that's great. Okay, so I'd now like to talk about some of the things. I've mostly talked so far about individual places, right? And I'd like to talk about now looking across a spectrum of different places, because we're now seeing the emergence of chemical and isotopic databases that are opening up the possibilities of making very broad-based synthesis studies. And one of the clever guys who is leading this field is Scott Jascheko. He recently moved from the University of Calgary to the University of California in Santa Barbara. And I want to mention a few things that we have been doing together. So we've been looking at what we can learn about transit times in catchments around the world. And of course, transit time is the time it takes rainfall to become stream flow, and that's an important controller of nutrient fluxes or contaminant transport or chemical weathering rates and other processes like that. And catchments don't just have one transit time. They have a distribution of transit times, as we saw in the previous discussions. And they have a distribution of transit times because the subsurface is heterogeneous and because rain lands at different distances from the stream. So they have these distributions that reflect the various flow paths that water can take to the stream. Now, one approach for estimating transit time distributions is to take a fluctuating signal of, say, isotopes in the precipitation and to mathematically convolve that with an assumed residence time distribution and then to predict the isotope signal you should see in the stream flow itself as the output. And doing this correctly requires typically very detailed data sets, so you can't easily apply it to a large-scale synthesis. But if we look at the isotopes of water, which are of course ideal tracers because they follow the water itself, The dominant signal in a typical water isotope time series is a seasonal cycle. Isotopically heavier in the summer, isotopically lighter in the winter, and as you go to the interior of a continent, like Russia, for example, then that cycle gets bigger and bigger. And so many studies have looked at the damping of a precipitation cycle, here in green, to become a stream isotope cycle, here this dark blue line, which is expanded here, and from the compression of the amplitude of that wave, we can calculate a mean transit time in this landscape of, in this case, about 1.5 years. And so we wanted to do this for everywhere on Earth that you can get these data. And there are about 250 rivers for which you can do these calculations. As an input, you can use the global network of isotopes in precipitation, and you have to interpolate, of course, between the measuring stations to figure out what these cycles must look like in precipitation in the other places where you don't have data. So if we do this analysis for rivers around the world, we come to the conclusion that that the average age of river water is, typically less than about 12 months. And when we got that result, we thought, well, does that make any sense? I mean, if we say that a typical catchment gives you about 1 meter of water per year, just as a round number, and the residence time of that water is a year or less, that means that there's only there's only a meter or less of water stored underground. And we looked at each other. He's a groundwater hydrologist. We looked at each other and said, if there's only a meter of water underground, why would anyone ever drill a well? There's not enough there to be worth drilling for. So it didn't make any sense. So we started thinking about this, and we realized that we had a problem. And let's illustrate this with a thought experiment. And the thought experiment is, imagine if we have a landscape that's divided into 2 pieces. And the one on the right has a short residence time. And so the one on the right will take a precipitation signal like this, and it will transmit that signal nearly completely. The landscape on the left has a much longer transit time, a more stretched out transit time distribution, and its seasonal cycle will be damped a lot more. And then the stream will mix the outputs from the slow and the fast part of the landscape, and it will give you this blue line, which is the mixed runoff. It gives you the seasonal cycle and the mixed runoff. And so the question is, if you compare that mixed runoff, which is all you ever have, you never have the individual pieces, you only have the mixtures. If you take this mixed runoff, will you correctly calculate the average transit time of the entire system? And the answer is you will not calculate the correct average. You'll get a strongly biased result, and here's why. In the underlying mathematics, you can show that the amplitude ratio between the stream and the precipitation varies from 1 if you are not storing any water at all. So it transmits precipitation directly if your catchment is made of Teflon, right? To a small number if your transit time is very long, okay? But this relationship is curved. So if our fast responding catchment is here and our slow responding catchment is here, then when we average the two catchments together, we will get a point that lies between these two catchments, but it's not on the curve. Okay? So the true mean transit time in this example is about 2 years. But we don't know this. All we have is the measured tracer cycle. And so from the measured tracer cycle, we will calculate a mean transit time that's much shorter. And we will underestimate the mean transit time by about a factor of 6 in this case. Now, this is called an aggregation error. It's an error created by aggregating together things that are different. And these errors are always there when you're driving, when your basic relationship is nonlinear. So the average runoff doesn't reflect the average transit time if you interpret that runoff as if it came from a homogeneous system. And you can't correct for that bias unless you already know how heterogeneous your system is, unless you already know that those 2 points are spread here and there. And you never know that. You don't know whether you have 2 points here and there instead, in which case you don't have a problem. So you can't correct for this. So you need instead to start asking yourself, in a heterogeneous landscape, what can we measure that averages correctly, that aggregates correctly? So we did another thought experiment. What if we have a catchment that in fact is partly covered with Teflon, so it transmits everything directly to the stream, and the rest of the catchment has deep, slow infiltration so that tracer cycles are completely eliminated. Right? Then the amplitude of the tracer cycle in the stream would directly measure what fraction of the catchment is covered with Teflon. Right? And that would be true regardless of how heterogeneous the catchment is. So it turns out that you can extend that very simple model to a very wide range of age distributions. And you can show that the amplitude of the seasonal cycle in the stream relative to precipitation does not reliably tell you what the mean transit time is, but it does tell you reliably what the fraction of that water is that's less than about 2 months. Now, about in this case means like 1.5 months to 3 months old. So it can tell you what fraction of your water is young. So we define what we call the young water fraction, and we show this can be reliably measured as the ratio of the amplitude of that cycle in stream water to the amplitude of the cycle in precipitation. And so here is an example of a real-world system in Switzerland where the young water fraction is in fact nearly 50%. And here's another system in Switzerland again, where the young water fraction is only about 10%. Yeah?
What about those catchments that don't have a strong seasonal factor? Because I guess there are places where you don't have really season and it's just...
Right, so if you are in the tropics near the equator, that cycle is much less. Yeah. The cycle in precipitation is less strong. You can't easily use this technique there. Or the other real problem is an island in the middle of the ocean, where the rain basically always looks like evaporated ocean water. And again, there is not much of a seasonal cycle. So to use this technique, you need an input signal. And if nature doesn't give you the input signal, it's too bad. So to verify this, we can do a series of Monte Carlo experiments with the computer models, where we know the correct answer from particle tracking in the model itself. And we can show very clearly that if you perform this technique, you get the right answer. On the other hand, if you try to use this to estimate the average transit time, you get this data cloud here of essentially totally unpredictable results. So, returning to the big question, how much young water is there in rivers around the world? Well, so across all of these rivers, we see that roughly 1/4 of river flow is younger than about 1.5 to 3 months. That the fraction of young water in rivers varies between nearly 0 and about 40%. And that this pattern is consistent across drainage areas of very small experimental catchments to some of the largest rivers on Earth. It's consistent in places where the water table is less than 1 meter below the surface and more than 200 meters below the surface. It's consistent in places where permeabilities are very low and very high, across a total range of something like 7 orders of magnitude. So it seems to be a thing you can say is generally true of a large number of catchments. And this behavior of the fraction of young water doesn't correlate with any of those variables. It does correlate with one variable, though. And you can see it if you look at this map. So the red dots are places that have very little young water. That is, they're mostly old water in stream flow. And the blue dots are places with more young water. And you can see that the red dots are mostly in the mountains. Now, what those data are telling you is that steeper landscapes have less, not more, less young water in their streams. And that is really a very strange result. But it's true. I mean, here is the diagram. If we plot the average topographic gradient in the catchment against the fraction of young stream flow, you see that steeper catchments have less young stream flow. And there's a lot of scatter there, but there is a relationship. So steeper slopes are correlated with smaller fractions of young water, greater permeability, and deeper water tables. And that seems counterintuitive, but we actually think it makes sense. I mean, your intuition says, well, steep landscape, the water must run off faster. But if you think about the geotechnical stresses underground, if we have a completely flat landscape, then all of the stresses are compression. It's just the load of the material above you. If we take that flat landscape and we make it convex like a mountain, then there is some net stress that is trying to open fractures. And you can model this. I mean, the geotechnical engineers can do this calculation. And it shows that the compressive stresses are smaller in a landscape that's convex than in a landscape that's flat. So in fact, in the steeper landscapes, you expect to have more open fractures, promoting deeper infiltration and longer, not shorter, transit times. We will skip that in the interest of time. The point of view that's emerging is one in which tracers and isotopes may not tell us anything about average water ages, but they may tell us something about the fraction of water that is older or younger than a specific threshold age. Now let's illustrate this with tritium. So you probably know that the Russians and the Americans, back during what they called the Cold War, performed this giant hydrological experiment where they put all this tritium in the atmosphere, right, by testing hydrogen bombs, because hydrogen bombs are also tritium factories. And so in the very faint gray here, you see the curve of tritium in the atmosphere on a logarithmic scale, okay? And a typical number these days is between 1 and 10, and back when Boris and I were young, it was about 10,000, okay? And since then, that tritium has been decaying with a half-life of about 12 years. And these black dots here show the concentration of that rainfall back then, corrected for its decay until roughly now. And you can see that basically all of the precipitation that fell before the atomic bomb testing has a concentration today of less than 1, and all of the rainfall that fell after the atomic bomb testing has a concentration today greater than 1, and somewhere around 6 or 8 or 10 or something like that. So what this means is you can use these two different age ranges in a sort of a mixing model that lets us analyze the fraction of our water, how did we quit? We quit because I pushed a stupid button. There we go. Whoops. And now we will simply fast forward. Very fast forward. Yeah, we will keep fasting. Yeah, here we go. We're almost there. Sorry. Somehow it's possible to mess this up. Right. So we can use these two end members to quantify the fraction of water that's younger or older than basically me, right? So younger or older than about 50 years. So we've compiled a database of isotope measurements from about 6,000 wells around the world. And if you calculate the fraction of groundwater that is younger than about 50 years old, you see that below about 70 meters depth, most of the groundwater is older than 50 years old. That is, the fraction that's younger than 50 years old gets small fast. So most of this groundwater is more than 50 years old. You can do a similar kind of analysis with carbon-14, except now, rather than saying younger and older than me, you're asking the question, is the water younger and older than humans in general, right? So roughly speaking, you're measuring the difference between water that fell before and after the Holocene. And again, if you take the world database of carbon-14 in groundwater, and you look and you group it according to different aquifers, you will see that the carbon-14, and you plot the depth. This is the depth in the aquifer that you need to go until half of your water is pre-Holocene. And you can see that depth is typically 100 or 200 meters. So if we go more than about 100 or 200 meters below the surface, most of that water is more than about 12,000 years old. Okay. Now that creates a real puzzle, because we've just said most of the water under our feet is really old. It's, older than me, that's really old. Or older than, the last ice age, that's really old. But the rivers that drain those aquifers are much younger, right? 1/4 of the flow in those rivers is less than 2 or 3 months old. How does that work? And the first thing to recognize is that it's only a paradox if you think that rivers and aquifers are well-mixed boxes where everything should be the same. And they clearly are not. So, if we start by understanding that the subsurface beneath our feet is very heterogeneous, right? Then there will be high conductivity parts and low conductivity parts of the material underneath our feet. The highest conductivity parts will, of course, transmit most of the water because they flow the fastest, right? And that water will be relatively young because they flow the fastest. And on the other hand, the low conductivity parts of the aquifer will have the oldest water because they flow very slowly. But that old water will be old precisely because it isn't going out to the stream. So the old water gets to be old because it's not flowing to the stream, and the young water appears in stream flow because it is the water that flows to the stream. So it doesn't require that the aquifer knows which water is old and which water is young and selectively moves some water or some other water. It's just the inevitable consequence of having different conductivity zones underground. Now there's one more paradox here. You can take all of the wells that have carbon-14 data, and you can group them in 3 different categories. You can say we have about 1,000 wells that might have all modern water from the perspective of carbon-14. Then you have another group where they must contain some fossil water because their carbon-14 is lower than a modern concentration. And then you can also see another category of these wells which must contain mostly fossil water. It must be more than 50% pre-Holocene water. That is, the carbon-14 concentration is less than half of what it would be in a modern water sample. If we then look within these samples at the presence or absence of groundwater that has tritium, we see that half of these samples that are significantly depleted in carbon-14 and therefore should be really, really old, right? Half of those samples also have tritium, which means they cannot be really old, because tritium has a half-life of 12 years. And if the half-life of carbon-14 is 5,700 years. So if you're anything like 5,000 years old, that's so many half-lives of tritium, there's nothing measurable left. So how is that possible? So it's only possible if aquifers are heterogeneous, and aquifers are heterogeneous. It's the basic fact of life. Aquifers are heterogeneous, so they can contain waters with a wide distribution of ages, even as sampled by an individual well. So what these data are showing us is that even in deep old groundwater, that groundwater must have some fraction of water that is only a few decades old, not centuries old, not thousands of years old. Okay. So what we've seen in this section is that we can see that we can reliably estimate the fraction of water that's young in stream flow, young meaning between 1.5 and 3 months. And we can see that this accounts for up to 40% of water in global rivers, but it only accounts for a tiny fraction of the water in global aquifers. And the calculation we skipped over shows you that that is less than 1%. On the other hand, most aquifer storage below our feet is probably decades or centuries or even thousands of years old, but that it's also perfectly realistic that we could have old aquifers that discharge young stream flow because those aquifers are highly heterogeneous. Okay. Now, I'd like to, in the last part of this talk, discuss some really new work. A lot of this is still unpublished. And we're looking here at a new way of asking an old question, which is, how can we use isotopes to understand the age of water and catchment processes? And I have a lot of collaborators here from the UK, from Germany, from Switzerland, and so forth, who have contributed significantly to this work. And I'll begin just with this picture of one of our field sites in Switzerland. This is what it looks like at low flow. This is what it looks like at high flow. And it can go from one to the other in about 30 minutes. It's a very, very reactive system. So at this particular location, we've actually built what we call a lab in the field. It's a little house next to the stream, and in that little house is a ion chromatograph to measure chemistry and a laser spectroscopy system to measure water isotopes, and we can do this every 30 minutes. We sample stream flow and analyze it every 30 minutes. Whenever it rains or snows, we analyze that. And so we're measuring at very high frequency these isotopic and chemical tracers. And here's a view of what some of those data look like. We're just looking at a few months during one winter. And you can see individual precipitation events and stream response. You can also see the snow accumulating and melting in this system. Here are the isotopes, and we're looking here at deuterium. The black line is the stream water. The blue lines is the precipitation. And these individual stacks of blue dots are individual precipitation events. So what we are seeing is that during an individual rainstorm, our deuterium concentrations can change by more than 100 per mil. The total annual variation in deuterium is less than 200 per mil. So you can have, during an individual day and an individual storm, you can have deuterium changing almost as much as you have during an entire year. Now, most of these samples are at very low volumes. So you still get a very clear signal of the total water from an individual storm. But there's tremendous variability in the input, and there's response in the stream. And we can look at individual storm events and see the individual dynamics of the precipitation, and we can see the stream responding to that. And we can even, for example, look at this one rain event where precipitation, the deuterium signal changes by 100 per mil, and the stream flow signal changes by about 20 per mil, and that's telling us that the stream flow is about 20% rainfall, just as a sort of a rough estimate. Okay? So we can do this for one event and another event and so on. But this led to the question, how can we think about data like this? And the conventional way to think about this is through hydrograph separation, to say that we have an old water component, which is represented by stream flow before the rain started. We have a new water component that's represented by the average of all the rainfall, and we watch the stream concentrations change, and we express now the stream water as a mixture of the old water and the new water as we go through the hydrograph, and we simply calculate by mass balance the fraction of water that is old versus new. And that works really well in some cases, and it works very badly in other cases. Here's an example where it doesn't work, where the old water, the rainwater, is dancing around the stream water concentration, so you cannot easily tell which is precipitation and which is stream water, or older stream water, in the mixture. And usually what happens in isotope studies is people just say, oh, we'll forget about that one. Or the very interesting cases where your stream water is here, your rainwater is here, and your stream went the opposite direction, which also happens. And people then just say, oh, never mind, we just won't look at that one. We call that cherry picking, right? So thinking about this problem, I realized that if we ask that question not about an individual rainstorm, but about a whole time series of months of data, that you can convert this equation, this is the classic hydrograph separation equation, you can rearrange this mathematically to create what I call an ensemble hydrograph separation equation that is simply a form of linear regression, where we are plotting on this axis the variations in precipitation isotopes relative to the stream. And on this axis, we're plotting the variation in stream water isotopes relative to the previous stream water. Okay? So it becomes simply a linear regression problem. Now, of course, we want to understand whether this actually works. And one way to test whether it actually works is to build a really simple mathematical model of a catchment, which nonetheless gives you nice complex behavior. And to use this to generate a synthetic time series where we actually know how much new water there is in our stream because it's simulated, and we know what the tracer concentration is. And then we can ask our analysis technique, what's the right answer? And then we can verify that against the model. Now, notice this does not require that the model is a realistic model of a real-world system, right? And I'm making no claim that it is a realistic model. I'm just saying it's a model where we know what the right answer is. And so we can use it to test a technique, which we will then take out into the real world. Okay, so here's some example behavior, and you can see that the fraction of new water, meaning the same day rainfall, new water in the stream is highly variable. And but it has an ensemble average, an average over that time period, and our method predicts exactly that line. We actually have two different lines there, and they're on top of each other, and you can't see the difference between what's predicted and what's observed. On the other hand, if we tried to use the mean transit time in the system as a predictor, we get nothing useful. So the mean transit time, the average age of the water, is just terrible as a predictor of how much water is less than a day old or a week old or a month old. Okay. And we can, as I said, we can test this not just for one event, we can test it for lots of events. And this analysis shows that if we use daily tracer data, this technique will tell us what fraction of the water fell as rain sometime today. We can apply the same thing to weekly data, which will tell us what fraction of the rain fell as water, what fraction of the water in the stream fell as rain sometime this week. And we can test these using the model. This is observed in the model versus predicted by the analysis. And so we can keep doing this again and again. We can also ask the question the other way around. We can say, what fraction of today's rainfall leaves in the stream today, or leaves this week, which is not the same question and not the same answer as asking that question about looking backward in time. So you get a different answer if you ask what fraction of today's rainfall leaves in the stream today, versus if you ask the question, what fraction of today's stream flow fell as rain today. And I know it sounds like it should be the same. It's mathematically not the same, and indeed you will verify in a model like this it's not the same. You can also do this analysis for individual slices of time. So you can ask, if we collect all the times when the flow is low, what fraction of the stream flow is young water then? If we take all the time when stream flow is high, what fraction of that stream flow is young? So we can plot this for different slices of the time series and get a trace of how the fraction of young water or new water varies as a function of total stream flow. And this may be a fingerprint of how the system responds. So, as an illustration of what you can do with this technique, here's a data set collected by a friend of mine, Chris Soulsby, who lives in a little village in Scotland. And once a week, he would get on his bicycle and put his little baby daughter in the back of the bicycle and ride around his town, and he would sample a set of streams near where he lives. And he had a rain collector in his backyard, and he would collect rainwater. And then he would take these samples into the lab, and he would analyze them for deuterium. Now you can't see, again, the rainfall dots here are very faint, but they basically fill this graph. Some of these catchments are mostly rural, they're mostly pasture or forest. And then we have some urban landscapes like this. And if you look at what the deuterium does in the stream, you will see that at base flow, these streams all do basically the same thing. But the difference is that at high flows, the more urban catchments have bigger variability. So if you apply the technique that I've just outlined to these catchments, you get this diagram. And you see that the fraction of new water, in this case it means water that's new this week, basically. The fraction of new water in the stream correlates very well with the fraction of urban land use in the catchment. That's not a particularly surprising result, since we know that streets and roofs on buildings and so on all generate fast runoff, right? But being able to quantify it this way is something relatively new. And if we used classical hydrograph separation to try to get the same result, what we will get are these numbers here. These numbers are all the same within their uncertainties. They all basically overlap. And so you just get a meaningless cloud of data from classical hydrograph separation. Here's data from another site in Scotland, where our colleagues have collected isotopes in rainwater and stream flow actually every day for several years. And you can see that the rainfall fluctuations are very strongly damped in the stream, but you also see that there's some dynamics there. And if we now construct a diagram where we're plotting as a function of average discharge at different flow regimes, what fraction of new water is in the stream, we see that this new water fraction varies from less than 1% to more than about 6% or so, like this. We can do the same analysis looking at the coupling between rainfall rates and stream flow rates. And that's not telling us how fast water moves through the system, but it's telling us how fast the hydraulic potentials of precipitation are propagated through the system. It's showing us how fast the pressure waves move through the system. And if we do that, we get a similar graph, but on a completely different scale. This scale runs from 0 to 30%, showing that at high flow in this system, if you put on, say, 10 millimeters of rain, you'd get 3 millimeters of runoff, right? 30%. But less than 1 millimeter of those 3 millimeters would be new water. That is, the new water fraction is always less than 10%. Okay. Here we go back to that place, Plinlimmon in Wales, where we have about 1.5 years of isotope measurements every 7 hours, with all kinds of really rich detail in those variations. And we can apply the same sort of analysis here. And we should see that at Plinlimmon, as you go from low flow to high flow, the fraction of new water, and this means now new in the last 7 hours, only rises to about 4%. But the fraction of the proportional stream flow response rises to something like 40%, indicating there's much tighter coupling between precipitation rates and stream flow rates than there is between the tracers in precipitation and the tracers in stream flow. Meaning that catchments, landscapes, transmit the pressure waves of rainfall events much faster than they move the water itself, which a number of people have understood for a number of years, but it's been very difficult to quantify. Now to our favorite place in Switzerland, this place called Erlenbach, where again we have some daily measurements of isotopes in precipitation and stream flow. And again, to remind us, right, Erlenbach goes through these really violent changes in stream flow. At Erlenbach, now, the fraction of new water in runoff can be as high as 20%, which is a lot. But again, the coupling between precipitation and stream flow rates is even stronger than that, and shows a very strong threshold effect. Now, you can generalize this approach. We're just a few slides away from the end. You can generalize this approach to look not just at the contribution of today's rainfall to today's stream flow, but also yesterday's rainfall, and the day before that, and the day before that, and the day before that, and so on. So just like if we look at one time lag, we have something that looks a lot like linear regression. If we look at multiple time lags, we have something that looks very similar to multiple regression. There are all kinds of mathematical details that are not truly multiple regression, but you can think about it that way for our purposes. So doing this, then, you can generate a transit time distribution, a distribution of ages, of how much water is 1 day old, 2 days old, 3 days old, et cetera, et cetera, et cetera. And this can vary greatly. These are model data here, of course. As we change the parameters of the model, we get very different shapes of these distributions. But in all cases, they're accurately estimated by looking at the synthetic tracer data in the model. So this indicates that this technique might work when we apply it to the real world. You can do the same thing, forward, you can do the same thing with the input-output data of rainfall and stream flow and get something like a kind of a unit hydrograph, which plots the system's response to a precipitation event. And again, this comes from this kind of multiple regression technique. The dark blue curve is the theory, the dots are what you infer from the calculations, looking backward from the data. And you can test that against a kind of a perturbation experiment. So the gray curve here is the model behavior, and the blue curve here represents giving this model system a kick, a pulse of rain every 5 days, and watching that rainfall pulse come out and watching the decay of that pulse. And if you add up all of those, you get a response function from the model, from the internal behavior of the model, and you can test that then against what the data are telling you when you simply look at a regular time series. Okay. Here's what you get if you do this with real-world data. This is this site in Scotland. This is the age distribution of the water in the stream as predicted by the isotopes in the stream. Here is the distribution of the hydraulic response in the stream. Notice the scale here runs from 0 to 30%. Here it runs from 0 to about 3%, right? So you can see that this is strongly peaked and much bigger than the signal representing the transmission of the water itself. Here's our favorite place, Plinlimmon. Here's the age distribution of the water that's coming out at Plinlimmon, at least for short times. There's obviously a long-term tail on this that goes out quite a long way. And here's the hydraulic response to precipitation events. And if we put these on the same scale, you can see that this curve here becomes that flat line there. So you can see that, in fact, the system is quite a lot more responsive in transmitting the hydraulic signal of precipitation than it is in transmitting the water itself. Here's, again, our favorite place, Erlenbach, and you can see, again, a totally different pattern of response in the water fluxes than in the tracers, again indicating that catchments and landscapes transmit pressure waves, transmit hydraulic potentials differently than they transmit the water itself. We'll skip that one. I'll just note that from this technique, we can also ask the question forward in time, what fraction of today's rainfall becomes stream flow today, becomes stream flow tomorrow, and the next day, and so on, and that we can get interesting answers from that, that again mirror the hydraulic response of the system, but at a very different amplitude. And this also for our 3 other sites. So, the general conclusion from this part of the talk is to show that there are new methods for using tracers to constrain timescales and mechanisms of storage, of transport, and of runoff generation on much shorter timescales. So we can now use tracers not just to ask how many weeks or months or years is the average age of our water. We can now begin to ask questions like, how much of our water is a day old? How much of today's rainfall becomes stream flow today? Or conversely, if we get another millimeter of rain today, what fraction of that millimeter will be generated as stream flow today or tomorrow or the next day? Okay. So I hope today to have shown you several different aspects of how we can use chemical tracers and isotopic tracers to probe the response of these complicated environmental systems across a wide range of timescales and to get a wide range of different insights into how those landscapes function. I think we will not, at least in my lifetime, be able to look in detail at the ground underneath our feet. Maybe in your lifetimes, I hope we make a lot more progress on this. But until we do, tracers that follow the water and tell us things about how long the water has taken to reach the stream, or what it has done chemically on its way to the stream. Those tracers will be one of the few tools we have for looking at the complicated, hidden landscape below our feet. So we need better tools for using those tracers to see that dark and unseen world down there. So thanks very much for your kind attention. If you have any questions, we can take them now. Or we can talk during a coffee break, obviously, also.
Kirchner, should I ask you, we speak about the basin kept a lot of water during a long time and realized it during short flood event.
Yes.
What do you think? Is it possible food basin work sometimes as amplifier? So provide the signal more strong than input. Runoff higher than rainfall.
Okay. That would be, of course, somewhat surprising. Normally, the way we conceptualize these things is that the stream flow is a function of storage. So to increase the stream flow, you need to increase the storage. But if you increase the storage, it means that you have more input than output. So it means you are not amplifying. But there's one very significant exception to that, which is, of course, in a snow-covered landscape, you can have warm precipitation onto snow, and you can generate more liquid water than your original rainfall. And you can do this actually in two different ways. One is, of course, warm rainfall melts snow. But if you calculate the energy balance for that, you see that you actually need a lot of rain to get a little snow melt. But the other thing that can happen is if you have water vapor that condenses into the snowpack, then the energy balance changes fundamentally, right? Because then each gram of water vapor that condenses to liquid water gives you 540 calories, and every gram of ice that you melt to liquid only takes 80 calories. So for each gram of water vapor that you condense into snow, you can melt 6 grams of ice into liquid water. So that's a multiplier of 6. So that's another way that you can potentially get more water out than the rain that you collect. There's another trivial example which I will mention, which is, of course, where you put your rain collector might not be an accurate average for the catchment. I had a case a few years ago where a graduate student from France wrote to me and said, "Professor Kirchner, I've studied your paper and I'm using it in my catchment and it doesn't work." And I said, "Well, that's very funny. I wonder what the problem is." I said, "Send me your data." And in his data, he had a catchment where the stream flow output was more than twice the rainfall input, not just for a storm, but long-term average. There's twice as much water coming out as going in. And the reason for this is it's a very steep mountain catchment, and of course, they put the rain collector down at the bottom of the catchment where it's easy, right? Not on the top of the catchment, and so they have a rainfall gradient and so on. And so I wrote back and I explained, well, you know, the theory is physically based. The theory conserves mass, right? Your data don't conserve mass, so of course this theory will not work with your data, right?
Thank you. I speak about around non-linear response of
Yes? Yes?
You say that the mobility of different parts of water content in the basin is quite different.
Yep.
But I think it's possible the mobility is changed related to content itself.
Of course, yes.
And in this case, the response could be stronger than I think so. Several years I developed the model of the way.
Okay. That would be very interesting. Obviously, there are very strong nonlinearities, particularly in unsaturated flow. Yeah, Sure, sure. Yeah.
More questions, please?
Yeah.
Does your presentation mean that the physically based model describes nothing?
Ooh, I will not go that far at all. No, I don't think that's true. I think, however, that, well, let me say it this way. I think we have learned a few things about some versions of physically based models that may not be accurate in some ways, right? So, for example, I showed in a few cases that representing the system as some kind of bucket is not useful if you are trying to simulate the age of water through the system, right? It might be completely adequate if all you care about is how much stream flow do we have, right? I mean, I at least believe, number one, all models are wrong, including mine. But number two, some models are useful for some things, right? And so models can be useful for some purposes, even though we know they are not correct in other ways.
But the focus physically based.
So physically based models, of course, that depends what we mean by physically based models, right?
All models are in a way physically based, and no model is absolutely physically based.
Yeah, I mean, the way I like to say it is, how should our models be based on physics, right? And in particular, the question I'm sort of shining a bright light on in a lot of this work is the question of how should we handle heterogeneity, right? How should we deal with the problem that our system is in fact, physically based. Our conductivity, our permeability, our soil retention curves, those things are all variable on the landscape at a scale that we cannot directly represent in a model, right? We can't build a millimeter scale model of a landscape. And so we need a way to let the models understand that heterogeneity or the effects of that heterogeneity without necessarily explicitly representing it everywhere. Now, In atmospheric science, people have this problem too, and they call it the closure problem. Turbulence. Turbulence is a horrible problem. You're never going to solve it in detail, right? So they create larger scale relationships that are based on the physics of what we know about turbulence and turbulent mixing and so forth. And those equations are physically wrong at the micro scale, but they're consistent with the correct physics at the micro scale, and they are reasonably accurate at the macro scale. And what we need in hydrology, what we need in physically based modeling in hydrology, is for people to think through that problem that way. And so to ask, I mean, at least I think the fastest way forward is not to ask, how can we solve Richard's equation and Darcy's law at the sub-millimeter scale, but instead to ask, what's the right equation at the 100-meter scale and at the kilometer scale if, in fact, at the small scale, we really have Richard's equation and Darcy's law at the 100-micron scale, right? How do we cross those scales to get realistic predictions at the larger scale? And I don't know the answer to that. I mean, when I was younger, I sort of was hoping I would make a lot of progress on this, and life goes by really fast. But I hope I have a few more years. I hope I can make some progress. I hope other people in this room can make some progress on this, right? Because it's where we need, I think, to make progress. The thing I will say is that what I did today was not talk about models, but to talk about data. And what I hope to have shown is several ways we can use data to test models. So a lot of the things I presented today are fingerprints of behavior in these systems, of how, for example, the fraction of young water scales with stream flow. You get more at high flow, you get in some particular pattern, right? That's a fingerprint. And a physically correct model should match that fingerprint. So we tend in hydrology instead to say, we will generate a time series and we will get a Nash-Sutcliffe efficiency, right? And whatever Nash-Sutcliffe efficiency we will get, we will say it's good enough, and then we can publish our paper, right? And the thing is that we can do that with models that disagree about the physics. And we can get very nice Nash-Sutcliffe efficiencies from all of them, which means you can't use that technique to decide which of these models is correct. They all win the beauty contest, right? So what I'm hoping is that we can develop more of these sort of diagnostic fingerprints, and that some models will disagree about those. So a lot of this has to do with detailed, fine-scale behavior. A Nash-Sutcliffe efficiency is mostly dominated by the really big patterns. Basically, if your model gives you storm flow at the right time, in roughly the right volume, you'll get a very nice Nash-Sutcliffe efficiency, even if the model does the completely wrong thing on the other timescales, right? And so I'm hoping that some of these fingerprints provide us with alternative tools for testing models, and gaining some insight into which physics makes more sense.
With this, I hate to interrupt.
No, no,
This is a
I've taken far
wonderful
too
talk,
long, but I thank you.
You're tired. We were all thankful to you. So
Thank you very much.